Unfortunately, that intro was what I planned to say for this first slide. So what I'm just going to say is that a computer or smartphone isn't magic. Like she said, it's a rock that we taught to think. I think that's awe-inspiring, and I hope that this talk, there was going to be a lot. If you get lost, just think of Princess Pow here. We'll come back to her. Um, okay, so I should start. First, what's thinking? That's up for debate, but for today, it's nothing but information processing that can adapt in pursuit of a goal. We're going to represent information using electrons because they're tiny and easy to move, and we'll process them by moving them and seeing where they end up. Once we can do that, it's just a matter of scaling up. So to move electrons reliably, we need a rock with an orderly arrangement of atoms, which nature provides as crystals. But electrons can only move if they have somewhere to go, and every material provides different bands where they can be. Some bands are full, so they can't move. Other bands are too hard to get to. So for electrons to move, we need a crystal with a band that electrons can move through. But we also have to stop electrons. If we can get a full band very close to an empty one, then we can bump electrons up into the empty band only when we want them to move. This is a semiconductor. All you need to remember about them is this. We can start and stop electron flow whenever we want without something clunky like a switch. Fortunately, one of the most common elements on Earth has these properties, silicon or beach sand. So that's our rock, and it's also where the name Silicon Valley comes from. We just have to melt it into a crystal, as shown here, dragging a melted zone through it again and again to squeeze impurities out like the last bits of toothpaste from a tube. So now we can move and stop electrons. But I haven't said how we do that. Because electrons are charged, we can push them with electric fields. Electrons also have their own electric fields, so we can move electrons using other electrons. That's the entire value of semiconductors, and pushing electrons, though, isn't quite thinking. So we'll modify our rock by literally shooting it with an ion gun. I think that's really cool. We do this as a regular part of manufacturing things. Anyway, adding ions in this way adjust the bands I mentioned, affecting how electrons move. So by carefully shooting our rock, we can make a structure called a transistor, which looks like this. Red and blue are where we shot a bunch of electrons into the empty band, so it's conductive there. We haven't done that in the middle, but if we add positive charge near there, we can pull electrons into our empty band and connect those areas. So you can forget about electrons now. What's important is that we've created something that can be on or off, called a bit, and our rock can actually turn on. Bits let us represent numbers. We can add another bit for 2. 2 and 1 would be 3. 4 would be maybe rude if you can see me, but you see the pattern. With 3 bits, I can show up to 7 now. 4 plus 2 plus 1. The next bit would be 8. Each bit increases by a power of 2, meaning you can count to 1023 on your fingers alone. Just don't. Also, a transistor, the circle up there, can represent a condition instead of a number. It can turn on a bit if it is on. 2 transistors can require one and the other, or one or the other, to be on. And using these conditions, if, and, or, and others, we can build logic. For example, we can use these to add 3 plus 3. Remember that 3 is just 2 bits that are on, or 0, 1, 1. Our logic circuit can say, if highest bit 1 and highest bit 2 are on, turn on the next higher one in the result. So we have a 1 at the start. Use that and again with the next bits, so the next one up is on in the result. And there's our answer, 1, 1, 0, which would be 4 plus 2 plus 0, which is 6. So already we're doing math. Now it's just a matter of scaling. Sets of addition circuits can make multiplication and advanced math. Further layers can reconnect math circuits on demand, so our rock can already do a lot. But we need to talk to our rock before this is useful. That used to mean cards with holes punched to mean 1s and 0s to start our logic chains, but now it means something like keyboards and monitors. In your phone, the location of each screen press is saved as a number, or a set of bits in a rock, which is then compared to a long chain of conditions, which are also bits. The result is another set of bits sent to the display, which acts as conditions to turn on pixels for you to see. So everything you see on a computer screen represents bits in a rock. That's all computing is, bits and conditions. We've already made complex logic out of that and applied that logic to translate between rock bits and our blunt human senses, which means we can talk to the rock and tell it what math to do. But we wouldn't say a rock is thinking yet, not when it adds 3 plus 3 or when it interprets 3 plus 3 from a keyboard, nor even when it beats a grandmaster at chess by analyzing the board according to rules that we set ahead of time. We seem to agree that a long series of if-then statements isn't thinking because it's predetermined. And we like to believe we have more control than that. But if we go deeper, we can give it control over its own bits and conditions and reward it when it does well. We can give it a number to optimize and then let it rearrange its own bits to see what works. This is, in a very real sense, learning. By trial and error, a rock can find a set of if-thens that enable them to play board games or diagnose cancer in ways that humans simply can't. When we look at the if-thens they come up with, they make no sense to us, but they clearly work. So is that thought? I mean, it's not always smart. One simulation tried to create an animal that moves fast, but instead made animals get really tall so they hit high velocities when falling over. But even that is clever and unexpected. Our rock is learning and coming up with genuinely new things. But we made it, we know its bits and conditions, so how can I call that thought? Best we can tell, that's all we are too. Connections between neurons form bits that reconfigure themselves based on external feedback, which our rock is now doing. Our brain is squishier than our rock, but fundamentally it's a set of self-reconfiguring connections, which means it may just be a matter of engineering before our phone needs meaning in its life in addition to charge. But let's rewind. We've taken a rock, turned bits on and off, used them to control other bits, and built from there until we had an existential crisis. Whether it's really thinking or not, these things are amazing. So when your phone is slow, just give it a second. It's pretty clever for a rock. Which reminds me, a guinea pig rescue in Portland has found the highest possible purpose to which our hyper-intelligent rock can aspire, which is naming guinea pigs. Since absurdism is the best defense against existential crises, I leave you with a list of names that a rock found fit to give to guinea pigs. Princess Pow, Fuffbee, Spackles, Afterpie, Dab, Pugger P, Snifkit. Okay, good, I'm done. Thank you.